Section 8.6 deals with numerical integration. In this section, we're going to learn two different rules to approximate the definite integral. Why would we want to do that? Well, that's because some functions, they don't have an antiderivative that's an elementary function. So there's functions out there, for example, number 2, the square root of x times the sine of x dx, there's no antiderivative that exists for it. For those functions, to approximate the definite integral, we can use the trapezoidal rule or Simpson's rule. Let's look at the trapezoidal rule first. The trapezoidal rule says, let your function be continuous on the closed interval ab. Then the trapezoidal rule for approximating the definite integral is that the definite integral is approximately b minus a over 2n times f of x naught plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3 plus plus 2 times f of x sub n minus 1 plus f of x sub n. And that's where n is the number of subintervals. So if we were to look at it as a picture, what's happening is that we're using trapezoids to approximate the area under the curve to the x-axis for a function f. Because we're using trapezoids, the sides in the middle get used twice, which is why you're multiplying them by 2. Before we look at Simpson's rule, we have to look at the following theorem. The following theorem says that if you have p of x, which is a function, ax squared plus bx plus c, and you find the definite integral from a to b of p of x dx, that's going to equal b minus a over 6 times p of a plus 4 times p of a plus b over 2 plus p of b. Now you don't need to have this formula committed to memory, but this 4 here is important because it helps explain where the 4 comes from in Simpson's rule. Now what Simpson's rule does is it places a quadratic, notice this is a quadratic, underneath the curve, so it does a best fit quadratic, and it finds the area underneath that quadratic. Looking at it as a picture, my function f is this black curve. Now what Simpson's rule does is it uses 3 points on your function f to best fit a quadratic, and then it finds the area under the curve for that quadratic. And it does that over and over again depending on the number of subintervals that you are looking at. So what is Simpson's rule? Well, Simpson's rule says let f be continuous on the interval from a to b, and let the number of subintervals be an even integer, because the number of subintervals must be even for Simpson's rule. Then the definite integral is approximately b minus a over 3n times f of x naught plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3 plus plus 2 times f of x sub n minus 2 plus 4 times f of x sub n minus 1 plus f of x sub n. Simpson's rule alternates between 4 and 2 inside of the formula because it's using those best fit quadratics to approximate the area under the curve. Again, this is where n is going to equal the number of subintervals, and for the Simpson's rule, you must have an even number of subintervals. So let's look at the following examples. Example 1 says to use the trapezoidal rule and Simpson's rule to approximate the value of the definite integral for the given value of n. We want to round our answers to 4 decimal places and then compare it with the result of the exact value of the definite integral. Let's find that exact value first. This is something I can integrate, so I know that I can just integrate it using the fundamental theorem of calculus. First, let's rewrite this. Let's factor out that constant multiplier. And then instead of x squared being in the denominator, make it a negative exponent, x to the negative second. If we integrate, we get 2 x to the negative first over negative 1, and that gets evaluated from 2 to 3. Rewriting that without the negative exponent, negative 2 over x, still evaluated from 2 to 3. Plugging in the limits of integration, we get negative 2 over 3 minus a negative, so plus 2 over 2. And we know that that's equal to 1/3, which is going to be to 4 decimal places, 0.3333. Now let's do the trapezoidal rule and Simpson's rule. To do the trapezoidal rule or Simpson's rule, for both of them, before you start, you need to figure out what delta x is, and you need to split up your interval. In this case, you know that you're going from 2 to 3. So that means that A is equal to 2 and B is equal to 3. Your subintervals are given as 4. Therefore, delta x is going to equal b minus a over n, or 3 minus 2 over 4, which is a fourth. Now, if you're looking at your interval from 2 to 3 as a number line, knowing that you're splitting it up into 4 different subintervals, you could split this number line up like this, and then determine what these values are, because this is where your x sub 0 is going to be, x sub 1, x sub 2, x sub 3, and x sub 4. And you're going to need to know what those points are so that you can plug them into the function. How do I get from 2 to the next one? Well, that's your change in x. That's your delta x, which is why you need to find that. If I take 2 and I add a fourth to it, so 2 plus 1/4 is 9/4. Adding a fourth again, that's 10/4. Adding a fourth again, that's 11/4. Adding a fourth again, we'd get to 12/4, which is 3. Let's also reduce 10/4, 5/2. So we know that x sub 0, or x naught here, is 2. X sub 1 is 9 over 4. X sub 2 is 5/2. X sub 3 is 11/4. And x sub 4 is 3. Now we can put them in the formula. The trapezoidal area is going to equal b minus a over 2n, and then it's going to be f of x naught plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus dot 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 plus 2 times f of x sub n minus 1 plus f of x sub n. In this case, we know that we are going to use 3 minus 2 over 2 times n, which is 4. And then it's going to be f of x naught, which is 2, plus 2 times f of x sub 1, which is 9/4, plus 2 times f of x sub 2, which is 5/2, plus 2 times f of 11/4, and then finally plus f of 3. If we were to put that in a calculator, well, remember the function here is 2 over x squared. Well, we would get, if I do alpha y equals for a numerator and denominator, that's going to be 3 minus 2 over 2n, so 2 times 4, and then times, remember the function is 2 over x squared. The first time around I'm plugging in a 2, so that's going to be 2 over 2 squared, then plus 2 times 2 over 9/4 squared, plus 2 times 2 over 5/2 squared, plus 2 times 2 over 11/4 squared, and finally plus 2 over 3 squared. All you did was plug in these values in place of your x in your function into the calculator. If we hit enter, we get that this to 4 decimal places is approximately 3352. So this is approximately 0.3352. Notice how close it is to the actual answer with just 4 subintervals. What about Simpson's rule? Simpson's rule said that the definite integral was going to be approximately b minus a over 3n, and then it was going to be f of x naught plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus dot 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 plus 2 times f of x sub n minus 2 plus 4 times f of x sub n minus 1 plus f of x sub n. In this case, Simpson's rule is going to be, well, b, remember, is 3, a is 2, and then 3, n is 4. And then it's going to be f of, well, the same values, 2, plus 4 times f of 9/4, plus 2 times f of 5/2, plus 4 times f of 11/4, plus f of 3. If we put that into a calculator, easiest way to do it is just to hit second and enter so that you have the same thing that you just wrote up. The only thing that's going to change is that you're going to make this 2 into a 4, this 2 into a 4, and this 2 into a 3. Going back here and just changing those numbers. Changing that into a 4. Keep going. Changing this number into a 4. And keep going. And changing this number into a 3. We hit enter, and to 4 decimal places, we have approximately 3334. So 0.3334. Again, notice how close this is to the answer using only 4 subintervals. Example 2 asks us to approximate the definite integral using the trapezoidal rule and Simpson's rule with n equal to 4, and then compare the results with the approximation of the integral using a graphing utility. Again, we're rounding to 4 decimal places. Let's first figure out what delta x is, and then split up our number line to find x sub 0, x sub 1, x sub 2, etc. So I know my a here is pi over 2, my b here is pi, my n is 4, and then my function here is going to be that root x sine of x. Delta x in this case is equal to b minus a over n, or pi minus pi over 2 all over 4, which ends up being pi over 8. If we were to grab a number line, starting out at pi over 2, ending at pi, breaking up into 4 subintervals, and this is going to be my x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. To get from pi over 2 to x sub 1, I know I'm moving delta x units. So pi over 2 plus pi over 8 is 5 pi over 8. Then this is 6 pi over 8, 7 pi over 8, and then I'd be at 8 pi over 8. If we want to, we can reduce this guy to be 3 pi over 4. Now we just need to put this into our formulas. So for the trapezoidal rule, we know that this is going to be approximately b minus a over 2n, so pi minus pi over 2 times 4, and then it's times f of pi over 2 plus 2 times f of 5 pi over 8 plus 2 times f of 3 pi over 4 plus 2 times f of 7 pi over 8 plus f of pi. Let's plug that into a calculator. Make sure that your mode is in radians. Checking real quick, I'm in radians, so make sure that you're in radian mode before you start. Again, we know that this was b minus a over 2n, so in this case pi minus pi over 2 over 2 times 4, and then it's going to be times the function's value at pi over 2. Recall your function is the square root of x times the sine of x. So we say the square root of pi over 2 times the sine of pi over 2, and then plus 2 times the square root of 5 pi over 8 times the sine of 5 pi over 8 plus 2 times square root of 3 pi over 4 times the sine of 3 pi over 4 plus 2 times the square root of 7 pi over 8 times the sine of 7 pi over 8. And finally, just f of pi, which is going to be the square root of pi times the sine of pi. Hit enter, and to 4 decimal places, I'm at 1.4299. So this is approximately 1.4299. What about Simpson's rule? Well, Simpson's rule is very similar. We know that what's going to change is, instead of 2 times 4 or 2n, it's a 3n, so 3 times 4. And then we know that these numbers are going to change from 2 to 4 when we're plugging them into the calculator. So we end up with pi minus pi over 2 divided by 3 times 4. And then it's going to be times f of pi over 2 plus 4 times f of 5 pi over 2 plus 2 times f of 3 pi over 4 plus 4 times f of 7 pi over 8 plus f of pi. Go to the calculator, hit second, and then enter. And then all you're going to be doing is changing those numbers, making these guys 4s and making this a 3. Making that a 4. Making this a 4. And then making this number down here a 3. You hit enter, and to 4 decimal places you have 1.4583. So this is approximately 1.4583. Let's see what the graphing utility, what the graphing calculator says the actual answer would be. If we were to put this into a calculator, we'd hit math and then 9. And then we say our lower limit of integration is pi over 2. Our upper limit of integration is pi. And our function was the square root of x times the sine of x. And we're integrating with respect to x. Hit enter. And to 4 decimal places, this would be 1.4579. The calculator is approximately 1.4579. Look at how close Simpson's rule is. It's off by the thousandth place with only using 4 subintervals. That's it for numerical integration.